So previously we saw that the state variable, nt, of a count process, which satisfies the Poisson postulates, is Poisson distributed with parameter lambda times t for an interval of length t. And this fundamental result is why we refer to the process by that name. Now this result allows us to calculate probabilities associated with the counts of a Poisson process for a given configuration of observation scheme and parameters, and this in turn allows us to make predictions about the trajectories of such a process. Now, since we allow the process to increment at any point in the continuum of time, it is now natural to ask questions about the statistics of the times at which the events we are counting that occur. More specifically, as we covered in our introduction to count processes, the so-called interarrival and arrival times of the process. So for today's lecture, we'll cover some basic results in this regard, and then we'll see that the resulting relationship between the dynamics of the process in the spatial and temporal domains allows us to actually construct a simple simulation scheme for homogeneous Poisson processes. So let's jump in. Right, so recall that if we write down the times at which we observe the state variable change, so the times at which the count increments, we term these times the arrival times or waiting times. So for the time we've waited for, say, the nth event to occur, we may refer to that as the nth arrival time. Also, we define the time that has elapsed between, say, the n-1th and nth event as the so-called nth interarrival time. Now, for purposes of analyzing the statistics of these quantities, we need to treat them as random variables. So formally, we define t1, so capital T1, as the random variable representing the time until the first event has been observed. Okay, and that will just so happen coincide with the first interarrival time, since we start counting from 0. Then we also define capital Tn as the random variable denoting the time between the n-1th and nth arrival time. Okay, so we then have the entire set, capital Tn for n running 1, 2, 3, etc., up to how many ever interarrival times there are, as the set of interarrival times. Okay. Now, as for the distribution of these random variables, we have the following theorem. The theorem goes as follows. The interarrival times, Tn, for n running from 1, 2, 3, etc., are independent, identically distributed exponential random variables with parameter lambda. Okay. Now the proof of this statement is as follows. If we observe that the event that the first interarrival time, so capital T1, is greater than some fixed time t, or lowercase t, coincides with the count up to that time t, lowercase t, being 0, well, then we can evaluate the probability that capital T1 is greater than some fixed t as just the probability of the count up to that point in time just being 0. So probability of nt equals naught. Now from our previous result about Poisson processes, we know that we can evaluate that as a Poisson probability, so we plug it into that distribution and we get out e to the minus lambda t, which is just the survival function of an exponential distribution. So it must be that capital T1 is distributed exponential lambda. Okay. And that thus takes care of the first interarrival time. Now, also, since the increments are independent, once the realization of T1 is observed, let's call that lowercase t1, then T2, so capital T2, the random variable, is again distributed exponential lambda. Now this follows since, well, again, the event that capital T2 is greater than some fixed t minus T1, which was the observed first arrival time, coincides with, well, the event that, well, nt minus nt1 is just 0. Okay, so the count in that increment after we've observed the first one is just 0. And thus we'll have that, well, the probability of T2 being greater than, say, some fixed t minus T1 is just the probability that nt minus nt1 is 0. And again, we plug that into the Poisson distribution using our previous result, and we'll again observe the survival function of the exponential distribution, And then we'll conclude that, well, capital T2 must also be exponential lambda distributed. And again, by the independence of the increments, we'll have that they're independent. And we can keep on going, right? And we'll see that, well, actually, all of the interarrival times are exponential lambda distributed. And that completes the proof. So we thus have that for a count process, which satisfies the Poisson postulates, its interarrival times are distributed exponential with parameter lambda. And all the results pertaining to the exponential distribution, so i.e. its moments, order statistics, and results like memorylessness, actually apply to the interarrival times of a Poisson process. Right, so what about the arrival times? Well, we reconstruct the arrival times from the interarrival times by defining a random variable, capital Sn, as the sum of all interarrival times, so the capital Ti's, for I running from 1 to n, and then we analyze the random variable, capital Sn, as representing the nth arrival time. So the notation, capital T and S, should now be more clear since we define the arrival times as a sum of interarrival times, so S for sum and T for times. Also, since we have just shown that the interarrival times are independent identically distributed exponential lambda random variables, we have that, well, capital Sn must be distributed gamma n lambda, right? Or Erlang n lambda, if you like. And this again follows from the relationship between the exponential and gamma distribution. And we thus have that accounting process which satisfies the Poisson postulates, so a Poisson process. The distribution of the arrival times for such a process are gamma. Right. So, in summary, if we go back to our data table, what this amounts to for a Poisson process is as follows. 1. If I ask you anything about the count or state variable of the process, you may analyze it using the Poisson distribution. 2. If I ask you anything about the arrival times, okay, in that table, you may use the gamma distribution to analyze it. If I ask you anything about the interarrival times in that table, well, you may use the exponential distribution to analyze it. Okay, and then finally, if I ask you anything about the categorical infinite column, well, that's a topic for the next video, but you get the point. We have nice, neat distributional results, which are all interrelated, but which we can use to analyze a Poisson process. Okay, and this neatly brings us on to our next little adventure, and that is populating our data table. More specifically, populating our data table with fake data by simulating a Poisson process trajectory. Now you might ask, what the hell is the point of faking data from a Poisson process? We're statisticians, we analyze real-world data, right? Well, one reason might be that you can simulate cool data sets for your students to analyze, for which you'll know all the answers, of course, since you know what the true data generating process is. But actually, the real motivation is that the simulation allows you to replicate the variation in a process by making multiple draws from a model process, which you can then use to calculate statistics, and more importantly, the variation in those statistics. Indeed, in the real world, we only get a single data set, and we have to calculate or estimate the variation in our statistics using calculus and theorems, and sometimes pretty dubious assumptions. But under simulation, we can do so directly using empirical techniques. As for how this applies to Poisson processes, well, you'll see that we can easily check our calculus by using simulation. So all of the results we use, we can actually check our results or our calculations using simulation. 2, simulation also allows us to answer quite complex questions under a given model configuration for which the calculus might be somewhat intractable. For example, continuing from our marathon metaphor in the intro, for example, what is the probability that a runner from VOB Running Club finishes before one from ATC, but not before one from Nedbank, and within 3 hours? Now, that's a difficult probability to calculate directly, even if you have a simple model such as this. But this is something that can easily be checked using simulation. Now, just a quick side note here. There are actually processes which, in fact, cannot be simulated exactly, which I'm happy to discuss if you're ever keen on doing a master's project with me, but I digress. Let's get on to the simulation. So the result that the interarrival times are independent exponential lambda random variables sets us up neatly for a simple scheme for simulating Poisson process trajectories, and by extension Poisson random deviates, and will distinguish between two modes of observation or simulation. The algorithm for the first mode, which we will term fixed count mode, is as follows. So we simulate exactly n events, hence fixed count, as follows. 1. Draw a set of random deviates, capital UK, from a uniform 0-1 distribution. Okay. Then set the interarrival times, tk, to -1 over lambda log lowercase uk. So where the lowercase uk's denote the realizations from those uppercase uk's. And then set the arrival times, sk, to the sum over all I running from 1 to k over all those ti, for k running from 1 to all the way up to that fixed n. Okay, so then 2, the count will be given by 1, 2, 3 up to that fixed n, and then the times, which will be random, are going to be s1, s2 up to sn for fixed n. Okay, and that concludes the fixed count mode. For the second mode of observation or simulation, which we will term fixed window mode, where we simulate a process trajectory over some fixed window running from, say, 0 to b, the algorithm is as follows. 1. Draw again all these UKs from a uniform 0-1 distribution. Set the interarrival times to -1 over lambda log UK. Okay, so we've simulated interarrival times. Okay, then construct the arrival times, sk, as the sum over all I running from 1 to k for ti, for all k running from 1, 2, 3, etc., all the way up to sum n star, where this n star is now the maximum n, such that the sum over all I running from 1 to n over the ti's is less than than b, which is the endpoint of that window. Okay, so we essentially simulate arrival times. We keep simulating them until we exceed the time window. So the last arrival time exceeds that window. Then we step one back, and then we set that as the last arrival time within that window. Okay, and then you can see that the count will then go in step 3, 1, 2, 3, up to some n star, where that n star is random, and the arrival times will be the random times s1, s2, all the way up to sn star. Okay, and we note that the fixed window mode of observation more closely replicates what we'll do in practice, since we'll typically observe a process over a fixed window of time. And there you have it. Simple as that. We have a simple simulation scheme in two modes of observation, namely fixed count and fixed window. And we can now replicate the dynamics of a Poisson process under each of these modes and then analyze the model process empirically. Cool. So let's look at some examples, and we'll look at applying the analytical results first, and then we'll take a quick venture into simulation. So here goes. So if we observe runners crossing the finish line of the Two Oceans Marathon, again at a rate of 0.4 per minute for some window of time. 1. What is the expected arrival time of the third runner? Okay, now we're talking about arrival times. How are the arrival times distributed? We saw that they're gamma distributed, or Erlang distributed. And well, what's the mean of that distribution? It's going to be n over lambda. Okay, do we have those elements? Yes, from the question we're looking for the third runner, and we have the rate parameter of 0.4, so 3 divided by 0.4, and then we see that, well, we can expect to see the third runner at around 7.5 minutes. Okay, simple enough. Question 2. Give a crude Vold interval estimate for the arrival time of the third runner. Okay, now what does crude or Vold interval mean? Okay, so crude, we're going to create a simple interval. Vold, it's usually when we apply some normal assumption or whatever. Actually, Vold interval might actually refer to something much more specific, but sometimes it's referred to as Vold interval if we apply some symmetry argument. We say, okay, let's suppose it's normally distributed, and we construct it as follows. Okay, so what we do is we say that, okay, we're going to take the mean and we're going to add and subtract 1.96, where the 1.96 comes from the quantiles of the normal distribution, times the standard deviation. of whatever variable we're interested in. Okay, so we go in, we plug in our parameters into that expression, and then we find a crude, and you'll see why it's crude now, fold interval of minus 0.98 to 15.98 minutes. Okay, so what that means is we can expect to see the third runner somewhere between minus 0.9 and 16 minutes since we started counting. Now you might say, okay, well that's a rubbish interval, right? Because you can't have negative time. And indeed you would be correct. But again, I stress that while we've applied some symmetry argument here, which is in fact not correct. So we have some assumption, the assumption is it doesn't actually apply, but at least this interval still gives us some information about the amount of variation. And we see there's quite a bit of variation, but ultimately not a very good interval, or at least not an exact one. Okay. Question 3. Give an interval estimate for the third arrival using R. Okay, so I'm being less specific here, but what we're going to do now is we're actually going to construct an exact interval. How can we do that? Well, it's because we know that the third arrival is gamma distributed. Well, why don't we just create an interval estimate by reading off the quantiles of that distribution, right? So we can have some idea of the variation in the distribution of the third arrival time. So how do we do that? Well, we apply the quantile function for the gamma distribution in R. So Q gamma, and then we plug in the probabilities, which we want the associated quantiles for. So 0.025 and 0.975, so for a 95% interval. And then we need to plug in the parameters, of course, so 3 and 0.4. Okay, and then we get out an interval of 1.54 to around 18. So what that means is we can expect to see the runner at around somewhere between 1.5 and 18 minutes since we started the clock. Okay, and that concludes our analytical examples. So let's move on to simulation. Let sim underscore Poisson P in lambda b be a function that returns a vector of arrival times, and we'll denote this vector as s, and then a vector of counts in t. Now, if the parameter n is specified, it will simulate in fixed count mode. Otherwise, if b is specified, so the parameter b, it will simulate fixed window mode. And both these modes will be conducted at rate parameter lambda. Okay, now we'll cover the code for such a function at a later stage, but for now we'll just look at how you can use the output from such a function to calculate answers to questions I present you with. Okay, so let's look at some questions. So for the 2 oceans marathon examples, using simulation, determine empirically the following. Question 1. The probability of observing more than 2 runners cross the finish line in 15 minutes. Okay, so that's just a question from a previous video we had, and we have an analytical answer for that. Question 2. The expected time until the third runner is observed. Okay, so we already saw this question earlier. Question 3. An interval estimate for the arrival time of the third runner. Okay, so again, something for which we have an analytical answer for. Okay, now what we're going to do is we're going to try and answer these questions empirically using, say, 10,000 simulated trajectories. Cool. So how do we do this in R, assuming that we have this function which will just give us the output if we provided the appropriate inputs? Well, let's tackle question 1. The probability of observing more than 2 runners across the finish line in 15 minutes. Okay, so we're going to have to say we've got 15 minutes, so we have to simulate in fixed window mode. Okay, so the way we do this in R is as follows. So first we need to create some storage. Why? Because we're going to run a bunch of simulations, it's going to give us some output, and we need to store it there. Okay, so we just throw store equals repeat NA 10,000 times. We're going to run our experiment 10,000 times. Then we run a loop for 10,000 iterations doing the following. Okay, so we run a simulation using sim underscore Poisson P. We set the rate parameter to 0.4, and we set the window endpoint to b equals 15, because we're simulating under fixed window mode. And then we take the results from that simulation, put it into some object called res. Okay, and then from that object, maybe we need to calculate something that we can store. Okay, and what we're going to do is, well, from that result, we're going to check, well, was the maximum count greater than 2? So in our particular realization of the process, were there more than 2 runners that crossed the finish line? store that result. And then we're going to repeat that process. And then we can use those simulated runs of the process to actually estimate the probability of the event that if we have more than 2 runners cross the finish line. Okay, and indeed what we do is we just set up an indicator, so the maximum of the count greater than 2, so just ask is that true or not, so that it'll then store it as a 0, 1, plug that into the store vector, and then we can calculate the mean of the store vector, and that will estimate a probability, right, because it's the mean of an indicator function. And indeed, if we run that, we'll see that we get out something which is approximately 0.94. Okay, so pretty close to what we had analytically, if you go back to the previous video. Cool. Question 2. Calculate the expected time until we observe the 3rd runner. Okay, now how are we going to do that? Well, one, I didn't give you a window here, so you may assume that I'm asking you to simulate in fixed count mode. Okay, so go back to our code, we set up our simulation again, so create some storage, so an empty vector, of length 10,000, then loop 10,000 times through the following procedure. Run a simulation of the process, okay, in fixed count mode, set the fixed count to 3, okay, using a break parameter lambda equals 0.4, okay, take the results, put that in some object called res, and then from that object, well, I don't know, record something which is useful for answering the question. And what are we asking? We're asking the expected time until the 3rd runner. So if we go through realizations of the process, well, let's just record the time that the 3rd runner crossed the finish line. Okay, we'll have multiple realizations, and then what we can do is we can just calculate the mean of that vector, and that'll give us an estimate of that statistic. Okay, so we do that, and we see that the mean time that we expect, you see the 3rd runner is around 7.4 minutes. Okay, so again, not too far off our analytical result. Cool. Finally, question 3. Calculate an interval estimate of the arrival time of the 3rd runner. Again, I haven't given you a window here, so assuming fixed count, so actually we can just reuse the results from what we had before. Okay, this time we're just going to apply a different empirical estimate to the store vector. Okay, and the thing we're after here are what? The empirical quantiles, okay, of our simulated runs. Okay, so we use the quantile function in R to do that. So we apply a quantile function to the store vector, and well, what are the quantiles we want? Well, we want them for the probabilities 0.025 and 0.975. Okay, so a 95% interval. And indeed, what do we see? Well, we estimate 1.5 to around 17.9 minutes is when we expect to see the 3rd runner. And again, this is not too far off the analytical results. So, pretty cool stuff. Okay, so that concludes the video for today. We have some nice results pertaining to the interarrival times, the arrival times, and also the state variable. And we saw that, well, because of the relationship between all of those variables, we actually have nice simulation schemes as well with which we can either check our calculus or answer more complicated questions. So I hope you found that interesting. As usual, I'll leave some problems up for you to check out, and then I'll see you in the next one.